All right, so in this video, I just want to cover one final thing before we actually do some examples here. What I want to cover is this exponential term, more or less just the RC part of it. I'm going to use my finer pencil so that I don't mess up this slide too much, and I'll go into a different color. How about I use green? So the RC here, for RC circuits, that is called the time constant, okay, for the circuit. Basically, the larger that RC is, or the larger that the time constant is, the longer that this growth or decay will take in order for the capacitor to reach its final value, okay? The same will happen in RL circuits when we get there, but it'll be a different time constant that involves the inductance, obviously, rather than the capacitance. But a lot of times what we'll do is we'll replace this RC with a Greek letter tau, and so that our equation looks like this. It'll just be the Greek letter tau. Okay, so it would be 1 minus e to the minus t over tau, and then you just know that tau for an RC circuit is equal to R times C, and it's different for an RL circuit, but the reason why we use tau, I'm going to go back to RC for now. The reason why we use tau is or why we use time constants at all is because time constants give us a fairly good approximate for when this behavior will settle down to its final value. Okay, if we think in terms of time constants, so let's say that I'm just going to write RC is equal to tau here. I want to go back to my thin pen. R times C is equal to tau. Okay, so let's say that in time, I'm looking at 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau here. Okay, so R times C has units of seconds. Okay, and so if I'm looking at this graph, and this is verifiable, you can look this up. I'm going to put these points on here. So the way that the expression works is after one time constant, or 1 tau, my RC circuit has already reached 63% of its final value. Okay, so at this time, it would be 0.63 times VCF already. Okay, that would be 63%. After 2 tau, it's already at 86%. After 3 tau, it's at 95%. 4 tau, it's at 98%, and at 5 tau, it's 99% of the way there. Okay, so the reason why this is important is because if we know our R and our C, which basically means we know our tau, then we know that in roughly 5 tau, our capacitor is going to be either fully charged, or in the case over here, it would be fully discharged. So it would be the same kind of thing going on over here, where we'd have tau, 2 tau, 3 tau, 4 tau, and 5 tau. And after 5 tau, it would be 99% of the way to 0. Okay, so it would basically be 0.01 of VCI at 5 tau. Okay, I just wanted to cover that briefly. I wanted to talk about what the time constant is, because sometimes you'll see it. You'll see the expression, like for example, you might see this expression written as VCI times e to the minus t over tau instead of RC. But you know for an RC circuit that tau is just R times C. Okay, and then we get into RL circuits, we'll talk about tau again and what the time constant is for RL circuits. But for now that we're now that's clear and we're on the same page about time constants, about tau, about charging and discharging cases for these circuits, I think we are ready to solve some examples. So I'm going to go ahead and end this video here. And in the next video, I'll go ahead and do a charging example and solve for some values.